okay. Voice.
Okay.
So live stream connect பண்ணிட்டு இருக்கேன் சார் 2 minutes.
Okay, okay. Audio ரொம்ப லோவா இருக்கு.
ஏ சைடுலயா சார்?
எஸ் சார்.
ஏ சைடுல ஆடியோ லோவா இருக்கா?
ஆமா ஆமா.
ஹலோ ஹலோ.
எஸ் சார்.
சார் இப்போ பெட்டரா இருக்கா?
ஓகே ஓகே. பெட்டர்.
ஓகே.
எஸ் சார், ஸ்டார்ட் பண்ணலாமா சார்?
எஸ் மேம்.
எஸ். லைவ் கனெக்ட் ஆயிடுச்சு சார். Good morning to one and all present here. On behalf of the group of RMK Group of Institution, it's my pleasure to extend a warm welcome to each one of you for today's generic talk series titled Mastering Data Structures and Algorithms, Your Roadmap to Engineering Excellence. We are truly honored to have with us Mr. Arvind Raghupathy, Senior Computer Scientist at Adobe. This session is a part of our continuous effort to bridge the gap between academic learning and industry expectation, and we hope all participants make the most of this opportunity. Now, I would like to welcome Dr. S. M. Uday Shankar sir, Head of the Department of Computer Science and Engineering Cyber Security, to deliver the welcome address. Please, sir.
Thank you, ma'am. Distinguished guest of today's program, Mr. Arvind Raghupathy, Senior Computer Scientist at Adobe, Bengaluru. Most respected Chairman, sir, Vice Chairman, sir, honored advisors, respected principals, deans, heads of departments, academic coordinators, faculty members, parents, and dear students of RMK Group of Institutions. A very good morning to one and all. A very absolute delighted to welcome each of you joining us today on YouTube Live for what promises to be an inspiring and enriching session. It is our great privilege to host Mr. Arvind Raghupathy for today's generic talk series on Mastering Data Structures and Algorithms, Your Roadmap to Engineering Excellence. As a senior computer scientist at Adobe with deep expertise in problem solving, performance engineering, and software architecture, Mr. Arvind brings a wealth of industry knowledge, both in practical and powerful. Sir, thank you for joining us today for sharing your valuable insights with our academic community. To everyone from RMK Group of Institutions, faculty, students, and supportive parents, thank you for tuning in. Once again, a warm welcome to all of you. Let us look forward to an insightful and empowering session ahead. Thank you and happy learning.
Thank you, sir. It's indeed an honor for me to introduce today's esteemed speaker, Mr. Arvind Raghupathy, who joins us from Adobe System Bengaluru, where he serves as a senior computer scientist. He brings with him with over 12 years of extensive industry experience, having worked across some of the most renowned technology companies in the world, including Adobe, Microsoft, VMware, and Motorola Mobility. Mr. Arvind has obtained his degree in information technology from Anna University. Over the years, he has built a stellar reputation in the field of computer science with his core expertise spanning across data structures, algorithms, scalable system design, cloud platforms, and full-stack web development. At Adobe, Mr. Arvind plays a key role in the design and development of large-scale, intelligent, and robust software solutions that impact millions of users globally. His journey through various technical firms reflects his consistent pursuit of technical excellence and innovation. Today, he is here with us to speak on a topic that lies at the very heart of computer science education: mastering data structures and algorithm, your roadmap to engineering excellence. This session promises to be immensely valuable for students who wish to strengthen their problem-solving abilities and prepare for competitive programming, internship, and placement. Let us join together in warmly welcoming Mr. Aravind Raghupathy, sir, and look forward to an engaging and inspiring session ahead. We welcome you, sir.
Yeah, thank you, ma'am. Thank you, sir, for the for extending the invite and the warm welcome. Ma'am, I would like to share my screen. I have a PPT that I want.
Yes, sir, you can go ahead.
I think I am blocked. The host isn't allowing sharing for this meeting.
Yes, I have made you as host now, co-host now, sir.
Okay.
Probably would be.
Okay. Let me know if everyone can see my screen.
Yes, sir, it is visible.
Okay, so I'm not going to repeat whatever ma'am and sir had already told about me. So the introduction that they gave was very, very in-depth and sufficient. So I'm going to move ahead from here and let's start by looking at what we are going to look at today. So in today's topic, we are looking at how data structures and algorithms will help you improve your engineering capabilities and help you better design better softwares, better systems, and also we will also finally touch upon competitive programming a little bit on that as well, and interviews. Okay. Moving on. So let's look at what the session is about. So today we're not going to be learning about each and every data structure, trying to understand what each every data structure does, and that's already covered as part of your academic probably. And there are other resources where you can also look up online and understand all of that. So what we are trying to understand today is why learning data structures is key in building efficient systems, efficient software, whether it is building a scalable backend or a front-end system, and trying to understand how these are foundational to ensure that all of these systems are scalable, robust, and performant. So before we move on, let's look at why this is necessary and what happens when you don't, have this understanding. So what happens like when, let's say, an engineer is working on the software industry for a couple of years, but he does not have an in-depth knowledge of data structures or algorithms. So the engineers tend to plateau. So when I say plateau, in the sense that let's say you have been solving problems or designing systems in a particular way and you don't know the foundations of data structures. You only know how to solve the problems, but you don't know how to solve the problems efficiently. And given the current market trend, what you need to distinguish yourself from others or other engineers is the understanding of how systems work and how you can design efficient and scalable solutions. So this is one of the key requirements in the current market, and it's also in the future upcoming markets. Okay, so before we start, let's look at how we are using data structures in real world without actually, thinking about it at all. So let's take an example of a library. Let's say you are in charge of a library to store books. Now, if you store the books as just a sorted order or a sorted list or a sorted order, every time you have to look up for a book, you will have to sort the data, get the use a binary search or any searching algorithm to look for a book in the sorted data, and just doing one level of classification on the data itself is not generally enough, because there are scenarios where you'll have to consider for different genres, different authors. So to improve this, what we do generally is we categorize the books based on genre, we categorize the book based on authors, and then we distribute the books around the library so that it is easy, and accessing anything from the library is very efficient. So this is an example of a data structure implementation that we are already doing in real world without even knowing that we are actually using a data structure. Now let's look at an example for algorithm. Let's take cooking. So when we are cooking a dish, we always need to follow the recipe. We cannot like alter the steps in the recipe to our liking, so that if we do that, the result that we achieve will not be the same as what is mentioned in the recipe. So imagine data structures are like the ingredients for cooking, without which we cannot start the process of cooking, and algorithms are like the recipe itself, which we follow to cook the dish and serve the dish. Okay, moving on. So let's begin with some basics. We'll start looking at what data structures are and what are the different types of data structures. So let's start with what data structures are. So data structures are nothing but a specialized way of organizing and storing data in computers so that it can be used efficiently. They define the layout, behavior, and access patterns for data. They are fundamental building blocks in software development. So let's say you want to store a list of numbers in your computer. You probably use an array for that. That is a data structure. Let's say you want to store uh, a list of a list of elements where you have weight or order or something like that associated with each element. Now that the efficient way to store that would be like a priority queue or a heap. That is another data structure. So at a basic level, what data structures try to determine is how data is stored. Like for example, there are some more complex data structures like trees, graphs, which help you in easy access and easy retrieval of data so that your system is more performant and efficient. Okay. Now let's look at some of the common data structures that are used in today's systems. We can start with arrays and lists. So arrays and lists are generally used to store data in a sorted order. Let's say, for example, in an order, not a sorted order, not always a sorted order. So let's say, for example, we want to store a list of users, for example. So you could store that in an array. So this way, reading the data would be efficient. Now let's look at the next one, stack and queues. So stacks and queues are nothing but a variation of arrays with some restrictions in how the data are added and removed. So another example is hash tables. Hash tables are nothing but indexed data storage. Like for example, when everything has an identifier or an index through which you can access it, that acts like a hash table. So let's say I want to access user data for a given user ID from a database. So every data in the database is indexed with that user ID, and that behaves like a hash table for you to use that index and then look up for the data. Now, let's say we are storing hierarchical data. So, for example, you are creating a file system or a visualization of a file system, something like that. So, for these, trees are helpful because trees have a parent-child relationship where a node acts as a parent and every node can have more than one child and each child can have more than one child. And this is a hierarchical system where data is efficiently classified. Now, the next one is graph. Graphs represent a data flow generally. Like for example, a route or a connection between one data to another data, and there will be some connection point. Like let's say graph will say this data is connected to this data by this. So it could be like this data is dependent on that. It could be that this data is required for that. So that's an efficient way of storing that information can be achieved with graphs. Some other data structures include heaps, tries, sets. So these are like sets are generally used to store unique values, and tries are generally used to store. Trie is basically a tree-like structure, but it has a n relationship where one parent can have n number of children. And heaps are used in storing or sorted or prioritized data, where the top of the heap you have a data with higher priority, and then in the bottom of the heap you have a data with lower priority. So these are some of the basics of data structures. And now let's look into algorithms. Basically, what an algorithm is nothing but a step-by-step procedure or a set of rules that are used to solve a problem. And in software engineering, algorithms are the logic behind how data is manipulated. Like, for example, when you're sorting, when you're searching, when you're optimizing, or when you're deciding between picking value A versus value B, or when you're updating a value based on what the user is responding to. So all of this is how is what algorithms define. At the core, algorithms define what needs to be done and how it is done, like a step-by-step procedure in helping you solve the problem, and how efficient the algorithm is, because these are all predefined steps or predefined instructions. They also come with all the memory computations needed for them, all the performance computations needed for them. So all of that is ready to use for you whenever you're using an algorithm versus when you're not using an algorithm. So now let's look at some of the common algorithms that are used across the industry. So we begin with sorting. So where we have different types of sorting algorithms. I'm sure you guys would have also read about sorting algorithms like bubble sort, insertion sort, counting sort, quick sort, merge sort. So what these algorithms determine are ways in which we can sort an incoming data, and each algorithm has its own time and space complexity defined. For example, for a bubble sort, your time complexity will be O of n square, where you are picking an element and deciding where it goes in recursive iterations until you reach the sorted output. So you keep swapping one element at a time and you keep sorting them. This is like a bubble sort implementation. And the space complexity that is used for is like O of 1, where you are the one space or the one space required to store the element that you're considering for the sort recursion is O of 1. Now let's look at a searching algorithm. So in searching algorithms include like binary search. So where let's say you have a sorted array and you want to look for an element in a given sorted array. So what you can do is you can divide the array into two, find out which half your element or your value belongs to, and continuously keep dividing until you reach your element. This is how a binary search works. So this is like a predefined algorithm that you can use to improve your searching algorithm. So generally, if you're looking for, let's say, an element in array or in a list, so what you would do, you will go traverse from the starting of the list, go element by element, and then traverse until you reach the end of the list, or you find the element. So what binary search tells you is like you can divide the array. Now determine whether your element will belong to the left half or belong to the right half, and keep dividing the array until you reach your destination. So this is another efficient algorithm that we can use. And recursion and divide and conquer are also used in binary search. And now coming to greedy algorithms. So greedy algorithms are algorithms where, like, let's say we have a set of possibilities. Like, let's say there are 10 ways to reach or 10 ways to solve a problem. A greedy algorithm is an algorithm which helps you efficiently decide which is the shortest path for solving that problem. So what the greedy algorithm does is like it picks the shortest path, tries to solve the problem, and if the path does not satisfy, it goes back and then picks the next shortest path and then begins solving the problem that way. And there are other graph algorithms which help you in deciding or computing cost, like Dijkstra's and depth first search and breadth first search, DFS and BFS. These are more like algorithms which are used for searching data within a graph-like structure. Okay, I just want to take a pause and check if anyone has any questions so far, or I can proceed.
No questions posted yet, sir.
Okay.
I think by the end of the session, we'll collect all the questions.
Okay. That's fine. Okay. Okay. Now moving ahead, let's look at a couple of technical case studies, which helps us understand how data structures are currently used in our today's systems. So for our first technical case study, let's look at Google Maps. So Google Maps helps millions of users find the fastest route, avoid traffic, explore places. But how does it actually do that? Behind the scenes, it uses data structures and algorithms. So let's try to break down what or how this looks like. So for this use case, let's look at how Google Maps, helps. Helps us find navigation and route details from a starting point to a destination. So let's say a user is opening Google Maps. When the user starts to search for a destination in Google Maps, it converts the starting point, which is where the user is, and the destination input that they have received from the user as nodes in a graph. And then what Google Maps does is it starts to find all possible routes from the start to the destination. So this is like a breadth first search algorithm where it runs a breadth first search across all the possible paths that it can form from the given start to the given destination. And then the next part comes in optimizing this, where it looks for the shortest path. Now, once we have all the possible paths, every path will, like, let's say we have like 5 ways of reaching from starting point A to destination B. Now, let's say each of the route has a specific weight or time taken in this case for the user to reach from A to B. Now, what the shortest path algorithm does is it looks for the shortest path while traversing through all of the given paths. So it will look at all of the 5 paths, identify which has the shortest time, and pick that and show that as a solution to us. Now let's look at how real-time updates are handled within Google Maps. Now for handling real-time updates, Google Maps downloads GPS info. Like for example, if I am using Google Maps and there are people ahead of me or people around me who are also using Google Maps, all of our mobile devices are synced with the GPS satellites of Google Maps. So we are constantly receiving and sending data to and fro from this Google Map satellite or server. So what it does is it takes into account all of the users' GPS data, all of the users. Let's say a user is marking at one location saying there is an accident. So any information, something like that, it also takes into account all of that. And when once it has all of this data, it feeds these data as real-time updates to all users of Google Maps. Let's say I am connected to Google Maps. I am driving from A to B. Now it will constantly, in frequent intervals, Google Maps will constantly keep updating the data that it has and with the data it is receiving. So that way, at every point or at every frequent interval, Google Maps will do a recomputation of my shortest path. So what happens? This is how Google Maps is showing you suggestions like a faster route is available. Do you want to take? And all of these are real time. So Google Maps will keep pushing these updates to users to continuously keep updating the real time updates to users. Now, in this case study, let's look at what are the data structures and algorithms that were used. So the graph data structure is initially getting used here to store information about various routes that are possible from the start to the destination. And we are also operating on the graph data structure by using a breadth first search. So what happens is once we have the graph data, like let's say I am the starting node and I have my destination as my destination node. So in my graphs data structure, the data is stored in such a way that from starting A to reach the destination B, what are all the edges that I need to visit. So let's say there are like 10 streets between A and B. So traversing from street A to street B, and then traversing from street B to street C, and so on. All of these are stored as datas in the graph data structure. So when my algorithm start, when I start the routing, so what happens is it goes and looks at all of the stored data for every edge to edge, and then it computes a defined path from A to B. So there can be multiple such paths, and so based on all the possible ways from which a user can traverse from A to B. It forms a list of all the possible paths and then identifies which is the shortest path. So identifying the shortest path is example of an algorithm used here. So here we use one of the any one of the popular shortest path algorithms to identify which is the overall shortest path that the user can take. And then when real-time updates come, let's say we have a flood of updates and which say that there are 4 new possible routes. To determine which route to show to the user, Google Maps uses a priority queue or a heap implementation where it will say, okay, every route or every update that is coming to me is a route with a priority or an order. Now, based on the highest priority, I will pick that and then show that to the user. This is like in overall how the Google Maps system currently works and what are all the different data structures and algorithms that are used in the Google Maps system. Okay. Moving on. Now, let's look at another technical case study, in this case of Netflix. So we're all, I mean, I'm sure that all of you all are very aware of Netflix, what Netflix is and what Netflix does. So Netflix is basically a streaming service where when you log in, it has content which is preloaded or which is content which is owned by Netflix and owned by others, which are preloaded or submitted to Netflix, and it allows users to view these content. It is similar to any streaming service where you pay a subscription to unlock access to various data and content. So let's take the example of how Netflix suggestions work. So whenever you open Netflix, it automatically knows what it needs to suggest to the user to watch. So how does it do this? So behind the scenes, Netflix uses some smart algorithms and efficient data structures to determine how it can curate suggestions for every user. Now let's look at let's try to break this problem down. So in graphs usage in Netflix, when you look at when a user loads Netflix, let's say in this case the user account or the user session, it is treated as a node and all the possible suggestions. Let's say I'm a user and Netflix wants to suggest 100 recommendations for me. So it treats me as the starting node and all of the recommendations or suggestions that it needs to show me as the destination nodes. So this is how the data is generally computed and stored in graph data structures. So for efficiently reading and using. So what Netflix then does is it starts to find all possible destinations that it can suggest to the user so that it can build its own suggestions list. Excuse me one second. So once it has all the information that it needs. So when I say information, I'm talking about the graph data structure, which holds, let's say from user A to user to my suggestion B, what are the possible ways or what are the possible routes that a user can take. When I say route, in this case, I mean like what are the possible things that the user will look at? Like, let's say a show that the user may be interested in, a new show that has come out or something like that. Those are all the routes that the user can take in this case. So this is different from Google Maps in that here the route becomes a suggestion, and that's how the data is stored in the graph data structure. So once the data is all available and ready for use, Netflix runs a BFS, a breadth first search algorithm, to look for all possible suggestions for my user account. So when I say breadth first search, what it means is like, let's say, let me give you an example. Let's say you are looking for a list of friends in Facebook. So what Facebook does is like it will go take your user account, look for uh, all your friends and look for all possible suggestions from your friends and build your suggestion tree like that. So when this is different from depth first search, where let's say you want to look for a possible path. In that way, you have to go look for a next path and look for the next path. So this is how the depth first search and the breadth first search are like different. So depth first search are generally used, like for example, in efficient route searching algorithms, where you have to find a efficient route from path A to path B, whereas breadth first search are used for a list of suggestions, when we are showing a list of suggestions to the user. Now, coming to real-time updates. So in Netflix also we get real-time updates, as in like whenever user is selecting a content or viewing a content, Netflix updates its own algorithms, or updates its own data based on users' usage pattern. So if I am viewing, let's say there is some content which I have viewed for 10 minutes and versus some content which I've been viewing for the next 1 hour. So what Netflix will do is it will rank both of them differently. So something that I watch for 10 minutes, let's say, is a lower rank compared to something that I watched for 1 hour. And something that I have selected will get a higher rank versus something that I watched only a trailer for. So when you hover on a tile or any show inside Netflix, it shows you a small trailer. So if you are watching only the trailer, that activity of yours will get a separate rank. When you're watching, let's say 10 minutes, that activity of yours will get a separate rank. When you're watching, let's say 1 hour of some content, that activity of yours will get a separate rank. So based on the rankings of the content that you are watching, like let's say you watch something for 10 minutes and something else for 1 hour. Now, the second thing that you watch for 1 hour will have a higher rank. So based on this, it will curate the possible suggestions. So let's say before you watched anything or before you did anything in Netflix, Netflix built a tree of suggestions for you. So it had like, let's say 100 suggestions. Now you have opened something or you have watched something in Netflix. Now what it does based on this, it will go and look for all the possible related content to the one that you have watched and update the suggestions list based on the ranking. Like let's say you watch something for 1 hour, it will rank that as let's say 100, and it will go and look for all the possible suggestions for related content from the content that you have watched, and it will rank them, let's say 90. And let's say you have not watched other content, but they are in your starting suggestions list, and they will have differing ranks based on, like when you're signing up, you select some user preferences. So based on that, they will give some rank to all of the other suggestions. So let's say they are like 70, 80, 60, something like that. So now your new suggestions list will include all the content from the related content of the content that you picked, because they have a higher ranking. So that has a ranking of 90. So your suggestions list gets updated with the new stuff that came in from the new ranking, and also from the stuff that was already pre-suggested, and you get an updated and a new suggestions list which is rendered back to the user. So let's look at what all data structures we are getting used here as well. So the what I explained already is that the graph data structure is used to build connections between user and content. So this is called as a this route is called as a suggestion, and this is how they are storing this data to build connections between users and content. And next is like for showing the real-time updates and for showing the most relevant update to the user. So they will be using a priority queue or a heap like implementation, which allows you to easily access the items from a list in order of priority. So let's say, like I mentioned earlier, let's say one content has a higher rank compared to a different content. So to read the content with the topmost rank or the highest priority, they will use like a priority queue to get this data, to store this data and read this data efficiently during real-time updates. Okay. So now that we have some idea about what or how, what data structures are and how they are getting used, now let's look at what we can do to improve ourselves in a way that, we think more in terms of building efficiently, building performantly, and how using data structures, or choosing the right data structure and algorithm can help you achieve this. So this is where every engineer needs to go for a mental model change. So this will be the number one requirement for every engineer, is to start thinking in terms of how to get, not how to get this working, but how best I can get this working, or like what, or not to identify the solution for a given problem, but to identify what is the best possible solution for any given problem, while also keeping aware of performance, scalability, maintainability, and basing your design decisions on all of this. So what we are trying to say here is, like, we need to start thinking in terms of performance, scalability, maintainability, to identify what data structure or algorithm will best suit my problem, rather than what is the easiest way to solve this problem. So once this mental model shift comes, our thinking will also start changing in a way that we start building for future, building for scaling, building for more robust and performant systems. This is where I think all of us are currently lacking, where we say we want to just build a solution for a problem. Like anybody can write a generic solution for a given problem, but identifying the best solution is where the key criteria for becoming a better and better over the years. Okay, so now let's divide whatever we saw in terms of performance, scalability, and maintainability, and look and try to identify what we can look for in each of them, or try to identify some try to look at some example use cases where making the wrong choices leads you into trouble, and how you can correct yourself. So for this, let's start with performance. So let's take a simple use case of a user login system. Let's say you're building a system where you have a user interface where you allow users to log in. Now, let's say for this user login system, you store all the data in a sorted array, or let's say an array or a sorted array. So when a user is trying to log in, for you to go and get, or for you to go and validate the user info, first you'll have to go look into the array. Either you have to traverse through the entire array if it's not sorted, or even if it is a sorted array, you will have to do divide and conquer, like a binary search, which we spoke about earlier, to get to the correct user. But instead of storing this in an array, let's say you store this in a hash map data structure. So in this case, what happens? Every user is assigned a unique identifier, and for you looking up a user, will be going and looking in the hash map based on the ID of that user. So whenever a user is trying to log in, you take the user's identity ID, or in this case, let's say, for example, in an email system, it will be in his it will be his email ID. You take that, and you create a hash map with that, and you go and look for that in the hash map. So that way, the lookup time for you, or for you to go get a user's data, will become constant. So this way, a lot of this way, the choice of data structure definitely and significantly improves significantly impacts the performance of the system that we are designing. Now, let's look at what are some of the key areas that we can look out for when deciding which data structure to build a performance system. So when deciding on the most performant data structure for your problem, we should look for answers to the following question. What is my most repeated problem? So whenever you are trying to solve, let's say you're trying to look for an element in an array, or look for, a value in a list. So every time your repeated operation would be to traverse from one value to the other value. And so this becomes my repeated operation. So first step will be to identify what is my repeated operation and how can I optimize that. So let's say you have some additional info saying that the data is sorted. Now you're doing an optimization on the way you're looking for the data, by doing a binary search instead of a linear search. So this is the first level of optimization that you're doing by identifying what the repeated problem is and how you can eliminate or reduce that repeated problem. Yeah, that's the next point as well. So the next point talks about reducing the number of repeated operations. Then there is also the next level of optimization that you can do where you cache the results of these repeated problems. So apart from, like, let's say we have reduced the number of repeated problems, but each problem is memory expensive or intensive. So this may not be very evident when you're trying to solve small problems, but when it comes to solving large problems with large data set, the number of times the problem is executed will matter, and so each time the problem executes will also matter, because each time the computation will be very memory expensive. So to reduce this, what we can generally do is, like for example, we can build a cache where we store results for the repeated problems so that we don't have to repeat or redo the problem again. So this is generally called as a memoization, or a memoization technique, where you create a hash table which stores all the results for various problems which you have already computed for. Let's say you're trying to identify a path from a node A to a node B in a graph, and let's say for identifying this path, you are going to consider 10 paths. And in each of these 10 paths, let's say the last four steps are repeating. Now, when you are calculating the first path, if you store the data for the path, the last four steps in a hash table, the next when you're considering the next path, when the next path also reaches the same starting point as this, like the when the next path also wants to say what is going to be my last four steps, you have already have the data computed in your hash table. So this way you can eliminate that extra repeated of computation of that path, and this will help in making your program more performant. And the next thing that you need to look for is, can I use any existing algorithm to solve my problem? So why using algorithms are better is, like, algorithms come with predefined time and predefined execution time and execution space. So that way we will generally be aware and conscious of what we are doing before we even start doing it. So this becomes very important in deciding how you are building your system for performance. Moving on to scalability. Now let's think of a scenario where we are creating a banking system. Let's say we are building a banking system where we allow every user to store their banking information. We store their banking information. We allow users to log in, look at their bank details, look at their bank balance and everything. Now let's say we create the user's bank balance as a small integer. The container for the user's bank balance as a small integer. That means that every user in the bank will only have 32,000 at the maximum, because small integer caps out at 32,000. So identifying what data structure can work for me is also very crucial, and identifying what data structure can cater to my future. Like, let's say I need to be able to store hundreds of crores or millions in terms of bank balance. So creating a container or a data structure, using a data structure that will account for that is also very important when you're deciding on what data structure to use. Another example is, like, for example, our IPL streaming service, Hotstar. So Hotstar needs to design their system in such a way that it can handle crores of simultaneous users. So the number of users who are logging in can increase and decrease. So let's say they have built their system to cater for, by guessing that they are going to have 10 crore users, they have built their system to cater for 10 crore users always. So what happens in this case is, every time the entire infrastructure is executing with its maximum performance power, and that will lead into more cost for them. So what they do is they build a dynamic configuration system where the system can increase in size and decrease in size based on the number of users. So this is like building a scalable architecture to account for dynamic varying user load. So this is an example for that. So when building systems let's look at what we need to look for when building scalable systems. When deciding on the most scalable solution for a problem, we should look for answers to the following questions. Will my data structure satisfy all my current needs? So first thing is whatever we already have, we need to ensure that we are able to efficiently store it, efficiently access it, while also considering for performance. So performance, whatever we consider for from the previous slide, all of that, and then we also need to cater to whether we can store all the data that we have without having any edge cases, unhandled situations like the bank balance use case, and optimize for cost. And all of these are considerations that we need to take for whatever we are trying to store currently. And also we also need to cater for what my future state will look like. Let's say in the future suddenly one day, or my data is going to go increase, or the number of users that are going to increase to 10 crores. Say let's say today is the final match. So I need to build a system which can handle the dynamic nature of the load, so that I don't have to go and update my system every time I have an edge case or an unknown. So this is like one of the things that you need to look for when you're trying to build a scalable system. Moving on to maintainability. So in every design, whenever we are designing a system, although we cater for performance, we cater for scalability, there will always be scenarios where you are encountered with unknown problems. Let's say, user decides to type, user is a Japanese user and you have not catered for any Japanese input, and the user is typing in Japanese. So this is a completely unknown for your system, and your system tends to generally fail at unknowns. Whenever systems are thrown an unknown problem, they generally don't know, or they do not execute that problem in a predictable manner, and this is where generally errors and bugs occur. So for another example, how picking the wrong data structure can affect maintainability is like, for example, let's say you pick a queue in place of where you need to be picking a stack. Now for you to achieve the same behavior of a stack, you will have to write some extra logic to convert the queue to a stack. So let's say tomorrow you want to create 100 of these stacks. Now all of your extra logic will execute 100 more times. So this way, for you to identify bugs, for you to identify issues in the solution will also become difficult, because the implementation logic itself becomes more and more complicated, where if you had initially picked the right data structure, it would have been much more simpler. So this is also one of the reasons why picking the right data structure also matters for building maintainable software systems. So now let's look at what we can look for when deciding what our design is going to look like when we are building maintainable systems. When deciding on most maintainable solution for a problem, we should look for answers to the following questions. Can I simplify my current solution by changing the data structure I have considered? So let's say you have already considered a data structure to solve a particular problem. So what we need to look for is, if I change this to a different data structure, is my solution looking more simpler? Does my solution become more readable? Does my solution, by becoming more simpler and readable, become more maintainable so that others can change it, or we can cater to new updates very easily? And that's the next point. So when you're deciding your design based on these factors, your design becomes automatically easily updatable, as in like whenever you want to change your design or update your design to cater for new scenarios or new things that are coming in, it becomes very easy. So these are some of the fundamental things that, fundamental model change that you need to bring into when you're trying to solve a problem for you to be, better or more efficient in solving these problems compared to what you are currently. So bringing it all together, so we have looked at how data structures shape performance, scalability, maintainability. But the bigger picture is once you understand all of this, and what will happen is once you have a good grasp of all of this, you will stop guessing and you will start designing. So that's why it is very important to understand all of these concepts and build your intuition for identifying the right data structures in the beginning itself, so that you don't have to revisit your design, and you build with an intention of being performant, being scalable, and being maintainable. So this needs to inculcate this. You need to inculcate this as a practice for how you would start or how you begin solving your problem, and look at all of the various criteria that we looked at before designing your solution. So that way, anytime you want to revisit or update your solution, it is easy, and your solution is capable enough to handle load or scale, and your solution is performant so that it gives the outputs back to the user efficiently. So let's look at how we can build this intuition. So mostly practice makes perfect applies here. So we need to rebuild known structures. We don't just read about hash map and let's say how the internal working of a hash map might look like. Let's try to build a hash map implementation by ourselves to understand how an hash map would actually work. Instead of simply using a map or a list, try to identify what each small piece in this data structure will look like, or how, let's say, a library, let's say you're using Java. In Java, they have built hash map as a library. Now try to understand how this library would work and try to build this library out by yourself. That will help you understand or fine tune your understanding of these data structures more. And let's say when you're doing the next step comes in identifying or building an intuition on what data structure to look for. Let's say you're solving a problem with a particular data structure. Just for the fun, just for the understanding or intuition building, go and try to build the same solve the same problem with a different data structure. That will help you compare both the data structures in real time, understand what are the pros each and everyone is bringing in, so that it will help you fine tune your problem solving when you are encountered with similar problems in the future. And at any point, watch for any possible bottlenecks or complexities that you're building. Let's say you're writing code, and the code is diverging and becoming more and more complex. Maintaining this or making updates to this in the future becomes very, very difficult. So at every point, stop and see if you can update your implementation to make it simpler, to make it more readable, and to make it more maintainable. These are like some basic things that you can look out for to build your intuition in solving more and more complex problems. The other advantage that you get by mastering data structures and algorithms and understanding each data structure and which can be used efficiently is that you're also building yourself or setting yourself up to excel in competitive programming. So all of these competitive programming competitive programming competitions generally use these as evaluation criteria. So generally in a competitive programming challenge, your maintainability, your scalability, and your performance are mostly used as evaluation criteria. So if you have modeled your brain or your thinking to always think about all of this when you're picking the data structure and algorithm for solving a problem, the challenge that comes to you when let's say you're in a competitive programming challenge is natural, and you don't have to prepare yourself anything extra for this challenge. So because you have already been thinking in these lines, it will come very natural to you. And the other advantage that you will also get is all of the top companies like Google, Adobe, Microsoft, all of them have data structures and an understanding and knowledge of data structures and algorithms as a basic criteria for clearing their interview. So when you are in a interview with with one such companies, the first thing that they will test you on is how strong your understanding of data structures are and algorithms are, and how efficiently you use it to solve the problem on the spot. So getting a mental model change to start thinking in these lines will help you with these as well. And now let's look at how you can get started. So the first thing for is to learn the fundamentals. Like I already told earlier, we practice makes perfect. We try to understand each and every data structure, try to break it down into small pieces, understand how each and every structure is working, what are its benefits, what are its drawbacks. And next part comes in identifying patterns in data structure usage. Like let's say, for example, you're solving a similar kind of a problem again and again, and every time you see that a particular pattern that you're using is able to solve the problem for you efficiently. Now that becomes a pattern that you have built in your intuition, saying that whenever I encounter a problem of this pattern, I will use the solution. So identifying these patterns and classifying themselves classifying themselves these patterns, and updating your knowledge on these patterns will help you quickly come to a decision, rather than having to solve the problem on the spot, build your into try to get it working and everything. So what I'm trying to say is, like, the more and more you build your intuition, the more and more it is easier for you to identify these patterns and use these patterns in problem solving. Yeah, and to to do this, what we do is we can go and practice coding challenges. There are a lot of online resources like Lead Code, Geeks for Geeks. There are many other sites as well. I'm not making an exhaustive list. I'm just giving you some examples. So a lot of resources available online to help you in understanding each and every data structure. In understanding what are the benefits, what are the drawbacks, and then putting it to practice by giving you some sample coding challenges. Like for example, Lead Code, I think probably has like at least 100,000 problems for you to solve, where solving each and every problem, you build the pattern, you build the intuition, you build the knowledge for data structures, and then you continuously keep evolving yourself as a better engineer. uh, I, that's all I had. uh, And I want to conclude by saying thank you all so much for listening. And if you have any questions, or if you have any data structure that you need some help with, or you want to dive deeper into, you can always reach out to me. And if you have any thoughts on the topics that we discussed, or if you have any questions that you want to ask, we can use this time to do that.
Yes, sir. Let us wait for 2 more minutes.
Yeah.
Ma'am, if there is no questions, you can wind up, ma'am.
Okay, sir. My
Very
student Kishan had a question. Just two
Okay.
minutes. So he's yes. We had a question from Madhu Karthik. How can advancement in machine learning and AI influence the design and optimization of traditional data structures?
Okay, so how can machine learning and AI, can you repeat the first part, ma'am?
Yes, yes, sir. Just a minute. How can advancement in machine learning and AI influence the design and optimization of traditional data structures?
Yeah, so let's say we have all of these design patterns and algorithms that we have already identified as things that work well and things that are efficient, and now we have a system called an AI system which is helping us in solve a lot of these problems more and more efficiently. So what can happen in the future is that, let's say, AI identifies a new or a different type of data structure, which the way the data is stored is different, the way the data is accessed is different, and the way the data is updated is different. So that way it can become more efficient, and it can affect the predefined preset patterns that we are currently following, and we could see a change in the patterns that are coming out of what advancements that we are making with this. It is a possibility, is what I'm trying to say, ma'am.
Okay, the next question would be, what role do distributed data structures play in handling big data in cloud computing environments?
Yeah. So it seems a little specific. So when you say big data, are you talking about big data systems or large size data? I just wanted to clarify on that.
Probably big data, sir.
Okay, so in when it comes to big data system, so what the entire the backbone or the architecture of a big data system works in such a way that, so there is like a data lake where all the data gets dumped. So the data size will be like in millions or billions of records. So every data from different source is dumped into something called as a data lake. Now the next step for us is to process this raw data. So all of the data needs to run through some processing logic. So what happens is these systems are built in such a way that the processing of the data itself are distributed in different stages and in different segments. So the overall the overall processing and the converting of raw data to process data is optimized by using these distributed system architectures, basically. So that's how they are optimizing for efficiency and converting your raw data to process data. And then this process data is further passed along to build visualizations, like for example, to build graphs, charts, trend analysis. All of this are using things like this.
One more last question. How can quantum computing reshape the landscape of algorithms and data structures in solving the complex computational problems?
Okay. Quantum computing, quantum computing itself is like, so what happened is, like, when we built our computer systems, like we were capable of, let's say, building our systems in such a way that we are able to solve, problems. But there are always some mathematical problems which are non-solvable. Like, let's say, these are like very mathematical problems which do not currently have a solution. And what happens is, when a quantum computer is able to solve all of these problems, we get answers to some of the basic science and engineering questions that we have been dealing with throughout. So that way, quantum computing can really affect the way everything is working. Like, if you're able, I mean, I'm not able to give you a real world example of a quantum problem, but there are a lot of these mathematical problems that reshape the way in which we think about physics, for example. So if a quantum computer is able to solve some, like, a physics problem which for which we currently don't have a solution, and based on our understanding we have we have written the laws and everything to understand physics in certain way, and now the quantum computer comes and says, I have solved this problem for you. Now you can update your understanding. So that way, quantum computing can, fundamentally shift in which how humans work, humans are interacting with tech. Everything can change, basically.
Thank you, sir. Hope students would have got the answers. I think the questions are over from the students' end. So, on behalf of the RMK group of institutions, I would like to extend our sincere thanks to Mr. Arvind Raghupathy, sir, for delivering such an insightful and motivating session on mastering data structures and algorithms. Your valuable inputs have truly inspired our students and added great value to their learning journey. At this moment, I would also like to take this opportunity to thank our management for their constant encouragement and support in organizing such knowledge enriching session. Last but not the least, heartfelt thanks to all the students and the participants, our respected principal, deans, and the faculty members for their guidance and coordination. Thank you all once again. Thank you, sir. I think we can wind up the session. Thank you so much, sir.
Thank you. Thank you all.
Thank you.